In this video, we'll take a look at the physics that govern the sounds we get from pipe instruments, which is the general term we use in physics for any instrument where the sound is created by making a standing wave in a column of air. So we're not vibrating a string on this one, which goes with string instruments, where we may have some piece that's vibrating, but the standing wave is actually on air itself. Now that column of air, we can make it longer or shorter. If you picture something like a trombone with the slide making the instrument actually get longer or shorter, we can think about that. Another way we can change the effective length for this column of air is to open or close valves or holes that expose the inside to the outside. So think about like a recorder. Has all the holes all the way along there. You put your finger over a hole and then it doesn't behave like a hole anymore. We've got just a closed up wall of the container then. So we get a standing wave that basically lasts from one open area to the next open area, or one open area all the way to the very end if it's closed all the way to the very end, or doesn't have an opening until the very end either. Just like with strings or with any other standing wave that we could imagine here, the boundary conditions, so what happens at the very ends of our medium, are going to determine the properties of the standing waves. How long they can be is the primary thing we're concerned with. For an open end or a closed end, we're typically going to think of these in terms of what the pressure can do. Remember, these are longitudinal waves, so it's kind of tough to make a diagram of what these would look like, but we can think about pressure. For an open end, we're just thinking about any part of the instrument, so at one end or the other, that is exposed to the air in the room. So at that open end, we've got all this air in the room around it that's all at some pressure, and atmospheric pressure is what we would call that. And so if at the very end of the instrument we tried to change that pressure, let's say we made the pressure a little bit higher, there's all this space around there where that extra air that's squeezed into this tiny space can expand into. So that increase in air pressure, it doesn't last. It gets corrected right away. The same thing happens for a low pressure area. If we have low pressure right at the end of the instrument, we have all this air around there that can rush in and equalize that pressure. As a result of this small change in pressure that's possible, we end up with effectively a pressure node at an open end. Pressure node. At a closed end, so for this one, think about like a slide whistle. We've got that slide that moves in and out along the tube, but it seals off the end of that tube. That makes this a closed pipe instrument. Something else would be a trumpet is a closed pipe instrument. So one end is open, the bell end is open, but the other end you're covering up with your mouth. And there's no little notch like we have in a recorder or a clarinet, something like that. There's no notch exposing the inside to the outside there. So a trumpet or a slide whistle, those are both examples of instruments that have closed ends. And on a closed end, we don't have any extra air around there to correct pressure changes. So pressure can change a lot at the closed end. So we'll think of those areas as pressure antinodes. You might also think about how much the air can move at each of these spots. That's a completely valid way to look at this. In that case, the open end, we can have a lot of movement. So we might call that a movement or a displacement antinode. And at the closed end, we've got the wall of the container, the closed off end, is keeping that air from moving any farther in that direction. We end up with a movement or a displacement node at a closed end. We'll stick with pressure, though, mainly because it makes our first set of instruments look very much like strings. So it'll make that a little bit easier to understand. So let's look at this first set of instruments that we call open pipe instruments. And when we say open pipe, we mean both ends are open. On the closed pipe, we'll have one end that's open and one end that's closed. With two open ends, we're going to now have pressure nodes on both ends of the pipe. So I'm just going to go ahead and draw those in. Pressure nodes on each side. And for my first harmonic, I'm going to have just a single antinode in between those. So either my pressure is going to be at a maximum in the middle, ooh, that's a little rough, or at a minimum in the middle. Then our next one, we're going to have two antinodes. That means we'll have an extra node right in the middle here. So we might have a maximum there and then a minimum over here. Or sometime later, we've got a minimum over here and a maximum over here. And for the last one, we're going to have three antinodes, which means two nodes in the middle. Something like this: maximum pressure, maximum pressure, or minimum, maximum, minimum. All right, so now the wavelengths on these things. Well, on the very first one, here we've got, let's see, either going from equilibrium to a high point back to equilibrium, or equilibrium to a low point and back to equilibrium. That's not a complete wave. To have a complete wave, we have to go equilibrium to a peak, back to equilibrium, down to a trough, and back to equilibrium. Or any point back to an identical point on these. So on this one, I only have half of a wavelength shown. So if I wanted a full wavelength, I'd need 2 times this distance. So my wavelength, and this is the wavelength of the first harmonic, so I'll write it as lambda 1, that's got to be equal to, well, 2 times the length of the pipe. For the second one, now I've got equilibrium to a high point, then back down all the way to a low point, to a trough, and then back up to the middle to equilibrium. That's a complete wave. So my wavelength for the second harmonic is just equal to L. For the third harmonic, looks like I've got even more of a wave showing here. Start at equilibrium to a high point, to a peak up here, equilibrium, trough, equilibrium, peak, equilibrium. That's one whole wave just to here, and then another half a wave there. So I need just the space from here to have a wavelength, or to have a complete wave, and that is 2/3 of this total space. So my wavelength on this one is going to be equal to 2/3 L. Now looking back at the frequencies, the wavelengths for harmonics on a string, we find that we have exactly the same allowed wavelengths here, which makes sense because we had the same boundary conditions as well. We said that we had to have nodes at each end, both on strings and on open pipes. So as long as we're talking about pressure and where the pressure nodes are, these look identical to the strings, and we'll have identically shaped harmonics. So that's all for pipes that are open on both ends. Now what if we sealed one end off, either with our mouth or we just, on the other end we had it sealed. So like a whistle is sealed on one end. You blow into one end, there's a little opening where you blow in, so that stays open, and then the other end is closed off. Or something like a saxophone, where you're sealing one end with your mouth, and the other end, the bell end, is open to the air. Those we call closed pipes, which is sort of a misleading name because they're actually closed on one side and open on the other. But we don't have any instruments that are closed on both sides, as far as I know. It'd be tough to make a sound on something like that if there's nowhere to move air into. But anyway, I think closed pipes, then we just need to remember open on one side, closed on the other. So again, we're going to think about pressure on these ones, and pressure is a node on the open ends, and it's going to have an antinode on the closed ends. So the first harmonic is just going to be the simplest wave that meets those boundary conditions. Node on the left side, antinode on the right side. This is going to be a little tough to draw on this scale, but something like this, and something like that. All right, now if we compare that to our earlier drawings, going from a node to an antinode and having that be our only section of the wave, that's like going from here to here, or here to here. And we said this whole thing that's shown is a half of a wave. So if we only go from here to here, that must be a quarter of a wave fitting in that space. So my wavelength then, for one complete wave, I would need 4 times that space. My wavelength is going to be 4L, and that's for the first harmonic. Now the second one that fits in here, let's think about the size on that. So back to this one. To begin with, we had half of a wave that fit into that space. Our second harmonic, we had 1 full wave, or 2 halves of a wave. And for the third one, we have 1.5 waves, or 3 halves of a wave. The fourth one, we would expect 4 halves of a wave, and 5 halves for the fifth one. So we're stepping up by 1 each time. In general, on these ones, I can fit n halves of a wave. So n is 1 here, 1 half of a wave fits in. N is 2, 2 halves of a wave fit in. N is 3, 3 halves of a wave fit in. So down here, if n is 1, we have 1/4 of a wave just from here to here fits in. If n was 2 then, we would expect 1/2 of a wave to fit in, and that would look just like this one, 1/2 of a wave. Now 1/2 of a wave either starts at a node and ends at a node, or if we looked at this section over to this section, we could start at an antinode and end at an antinode. But that doesn't fit with the boundary conditions. We have to start at a node and end at an antinode, or vice versa if we're looking at the other direction. So on this one, actually the second harmonic just doesn't fit. We don't get the second harmonic on closed pipes. We'll run into the same problem with the fourth harmonic and the sixth harmonic. We find that only odd-numbered harmonics fit with these boundary conditions. So, first harmonic, I got 1/4 of a wave in there. Third harmonic, I'm going to get 3/4 of a wave. So it's going to look something like this. So I've got half of a wave here, and then another 1/4 of a wave here. That gives me 3/4 of a wave altogether. 3/4 of a wave fit into that space. Let's see, how much space would I need for a full wave then? Well, I guess I would need the length of this plus another 1/3 of that length. And so my third harmonic, I find that I would need 4/3 of that length in order to fit. And you might see the pattern here. When n is 1, we had 4L, or 4/1 times L. When n is 3, we had 4/3 times L. When n is 5, we're going to get 4/5 equals L. Let's draw it though, and we can verify it that way. So on this one, I'm going to have 5/4 of a wave fitting in there. So I'm going to have an extra node and an extra antinode in here. So maybe a node about there, one about here, close enough anyway. Something like that. So on this one, I have 1 full wave and then another 1/4 of a wave fit into that space. So let's see, 1 1/4 is 5/4. So for 1 wave, I would only need 4/5 of that space L. So lambda 5 is equal to 4/5 L. Now, on the AP exam, they don't ask you to memorize any of the equations that your textbook has for the wavelength or the frequency of the nth harmonic in a string or in a pipe. So my expectation would be they're looking for more of a conceptual understanding, doing things like this, being able to sketch out the third harmonic in a closed pipe and determine the frequency from there. So something like this, we could then draw this out, the third harmonic. We could figure out the wavelength of the third harmonic. Maybe they'd give you a value L. Figure out the wavelength of the third harmonic. Then maybe they give you the speed of the wave, so it's just the speed of sound in here. And then you could take your wavelength, and you could take your speed and find frequency. Something along those lines is what I'd expect you to see on the AP exam. Well, that's all for this one. I've got another one following shortly about beats. That'll be a much shorter video. Be sure to check that out. If you learned something from this video, please like it. If you think you'll learn something from future videos, subscribe, and I'm always open to your comments. Thank you much.